In this video, we are going to introduce time domain analysis or time response analysis. So here this time domain analysis or time response analysis is very important in control systems topic. Why? Because whatever the signals we are going to consider in time response analysis or time domain analysis or varies with time. So here whatever the signals you are considering like R of t as reference input, C of t as control output, so all those you are taking with respect to time. So that's why this time analysis, time domain analysis or time response analysis is very important. Then what is meant by this time response analysis means, so response is nothing but output of the system. So time response analysis is nothing but variation of the output of the system with respect to time is called as time response analysis. That means, so if time is varying, so with the time what is the variation of output of a system? So that means we need to see the variation of output C of t. So that is called as time response analysis. With this time response analysis, we can study the stability of the system, accuracy of the system. So we can study the system by using this time response analysis. So this is very important throughout the control system. How we will calculate this time response means, time response is nothing but output with respect to time. So up to now we discussed our output in terms of transform. That means we consider as frequency domain. Frequency domain of the output up to now we considered in our previous videos to calculate transfer function or gain. So that means you consider C of S. But here time response analysis, so you are going to calculate your output with respect to time. So that is meant by the output in time in terms of time C of t you are going to calculate. So here I am going to consider a control system. So here I am having a control system like this. So here I am giving a signal R of t. So now here I am having a gain. This is open loop gain G of S, and here you are having C of S. So here as previous you just consider like transforms. Why? Because your open loop gain and forward path gain, if they given in terms of Laplace transform, then here R of S is the input transform, output transform, open loop gain, and feedback gain if you consider that is equivalent to H of S. So this is a negative feedback control system. This is a negative feedback control system. For example, if you want to do time response analysis for this system, you need to find out the output. So how will find out the output? How will find out the time response analysis means, so you need to get the output with respect to time. That means you need to get C of t. So here that from the knowledge of negative feedback system, that the transfer function T of S is equivalent to C of S by R of S is equivalent to, so G of S divided by 1 plus G of S into H of S. So this is the transfer function of this negative feedback system. So that means, so open loop gain divided by 1 plus open loop gain into feedback gain. So this is the transfer function of negative feedback system. Transfer function is nothing but output transform by input transform. So by this I can write the equation for C of S. C of S is equivalent to R of S into G of S divided by 1 plus G of S into H of S. So ultimately to get time response, so how we will get? So time response means output with respect to time. That means you need to get C of t. For that, take inverse Laplace transform on both sides. So you will get C of t is equivalent to La inverse transform of R of S into G of S divided by 1 plus G of S into H of S. Like this way we can get our time response of this system. So now coming to types of response. So here we are having two types of time responses, that is transient response and second one is steady state response. So transient response is nothing but response of the system which varies with time. So coming to steady state response, so steady state response of a system won't change with time. So it will come constantly. So for example, if you are having any response C of t like this is t, and on y axis I am going to consider C of t. If your response is like this, so up to here it is varying. From here to here this is constant. So this is called as transient response. So from here to here this is transient response of the system, and steady state response of the system. From here to this constant value where you will get up to where you are going to get this constant value. So up to that point, so that is steady state response. That means, so you can observe here, so this response is varying with time. If you are increasing your time, this is going to vary. But here in this place, if you are varying time also, your response is not going to vary. It is like a constant. It's in steady state. So this is transient response, this is steady state response. We are having two types of responses here. So we'll have two types of responses here. One is transient response which varies with time, and another one is steady state response which won't vary with time. As the name indicates, it will have a steady value like this. So the best example response for these two responses is like this. If your time response or output of the system is like this, then up to here we can say that is a transient response, and up to from here to that steady state value you will call that as a steady state response. This is about introduction of time domain analysis and time response analysis. We can call it as time domain analysis or time response analysis. This is very important chapter, you can say, in terms of GATE. So we will get some 2 marks questions, 1 mark questions from this unit. In this video, we are going to discuss the test signals in transient analysis. So we discussed that we are having two types of analysis, that is transient analysis, second one is steady state analysis. When you are doing transient analysis, you need to know about the test signals. These are the best test signals you are having. So in the topic of signals and systems also, we discussed that impulse and step are the very best test signals to test any system. Here we are adding two more signals, that is ramp signal and parabolic signal as test signals. The characteristics of this test signals is they undergo sudden shock, sudden change, and they or having a constant velocity and constant acceleration. These are the characteristics of these test signals: sudden change and sudden shock, and you are having constant velocity and constant acceleration. These four are the characteristics of this test signals. Coming to these signals, we are having impulse, step signal, ramp signal and parabolic signals. So we know the definitions in the topic of signals and systems. We know clear definitions of each and every signal. So but here also I want to give the same definitions. So here coming to impulse signal, this is always represented with del of t. Del of t is always is equivalent to 1 when t is equivalent to 0, 0 when t is not is equivalent to 0. So del of t is nothing but a impulse at t is equivalent to 0. So this impulse with amplitude 1. So this is del of t and this is with respect to t. And coming to step signal, so sometimes we will call it as unit step signal whenever amplitude is equivalent to unity, but here I am calling this as just a step signal. When I call it as just a step signal, we need to consider a amplitude or any voltage. So that means, so here I am going to represent with u of t. This step signal I am going to represent with u of t. U of t is equivalent to some amplitude a when t greater than or equal to 0 and 0 when t less than 0. So this is the definition for step signal. So when we will call it as this step signal as unit step signal means whenever amplitude is equivalent to 1, when a is equivalent to 1, this is called as unit step signal. So the diagrammatic representation of this unit step signal will be like this. So this is u of t and here the amplitude is a. So if it is a unit step signal, the value of a is equivalent to 1. So with respect to time, 0 to 0 or greater than, it will give an amplitude, but if you consider below 0, so you are not going to get anything. That means the value or amplitude or voltage below 0 is equivalent to 0 for unit step signal. So now here we are having ramp signal. So always we will represent with r of t. R of t, the definition of r of t is equivalent to some at when t greater than or equal to 0, 0 when t less than 0. This is the definition for ramp signal. So the structure of image of ramp signal will be like this. So when t greater than or equivalent to 0, you are having signal like this, linear increasing signal like this. So when we will say this is a unit ramp means whenever your value of a is equivalent to 1, that is called as unit ramp signal. So the definition also going to change like r of t is equivalent to t when t greater than or equal to 0. If the amplitude of that ramp is equivalent to unity, then you can say r of t is equivalent to t. If your ramp is having some amplitude, then you need to consider the definition like this. So now here coming to parabolic signal, I am just representing this parabolic signal like x of t, and here the definition of x of t is equivalent to a t square by 2. If your parabola is having some amplitude, then this is equivalent to a t square by 2 when t greater than or equivalent to 0 and 0 when t less than 0. This is the definition for your test signal parabola. When you can say this is unit parabolic signal means whenever a is equivalent to 1, then your parabolic signal is used to call it as unit parabolic signal. Shape of this parabola will be like this. The shape of parabola will be like this. So this is 0 to t, so it will give us a t square by 2. So if a is equivalent to 1, then you will get the definition as t square by 2 when t greater than or equivalent to 0. Generally you will consider unit parabola. So here this is unit parabolic signal x of t. Now below 0 you will get 0. You are not having anything. So now here how you will get this shape means, how you will get each and every shape means, you just take the values of t and you just substitute the t value here. You will get some points. You just take a graph paper, you just take the values of t and you just apply in this definitions and you just mark in y-axis with respect to x-axis. So you will get this same shape. So now these are the definitions of our test signals. So coming to the relations between these test signals, the relations between the test signals. So before relations, I want to consider the S domain. These are the time domain relations. This is time domain. So if you want S domain, so that means transform of these signals. So here the impulse function del of t transform, you know that the transform, any transform, either that is Fourier transform or Laplace transform or jet transform of unit impulse function is equivalent to 1. So in S domain the transform is equivalent to 1. Coming to step signal u of t. So u of t is equivalent to a. So for u of t, the Laplace transform is equivalent to 1 by s or a by s. If you are having a here, you need to consider a by s. If a is equivalent to 1, you need to consider 1 by s. This is for unit step. This is for unit step transform. This is for step function transform. If you are having amplitude, in S domain also you will get that amplitude. Similarly for ramp signal. So for ramp signal, so the transform is 1a by s square if that is simple ramp. If that is a unit ramp, the transform is 1 by s square. Coming to ramp parabolic signal. So the transform of parabolic signal is equivalent to a by s cube. If you are having unit parabola, then the transform is 1 by s cube. These are the frequency domain values for this test signals. Coming to the relations. So what is the relations between these test signals? If you see, impulse is nothing but 1. So if you consider integral 1, then you are going to get u of t. Integral del of t. So integral del of t is always equivalent to u of t. Integral u of t is equivalent to r of t. That means integral of 1 you are going to get t. Integral of a you are going to get at. So like that, integral r of t is equivalent to parabolic function. We represented with x of t. So I am going to consider like this. By these equations, if you want del of t, then you need to take d by dt of u of t. D by dt of u of t is equivalent to del of t. D by dt of r of t is equivalent to u of t. By this equation, I am just sending this integration to that side. And like that, d by dt of parabolic signal x of t is equivalent to r of t. Or if you want to write del of t in terms of r of t. If you want to write del of t in terms of r of t means you know that by these relations you can write any test signal in terms of any other test signal. So I want to write del of t in terms of r of t. I am considering this del of t is equivalent to d by dt of u of t. But we know that u of t is in terms of r of t. So I am replacing that d by dt into in terms of u of t. Here in place of u of t I am replacing this d by dt of r of t. So d square by dt square r of t will be the relation between del of t in terms of r of t.